All right. My name is Jared Poche. This is my session for the evening, one byte at a time, deleting millions of rows from production systems. I thought that sounded like a suitably intimidating subtitle.
Yes, it does.
So, about the author, my name is Jared Poche. I've been working with SQL Server for about 20 years now. I began teaching certification classes in a community college in like 2002. And then I like to say I worked for a little company called Microsoft for about 10 years. And I was a I specialized in performance and storage engine topics. Since then, I've been working as a database engineer at a couple of places. My current stint is with Channel Advisor. I think I need to update some numbers here. I've spoken at SQL Saturday regularly, but mainly within the region, and I'm coming to you live from Raleigh at the moment. So I've mainly spoken in Raleigh and Charlotte. I've also spoken at PASS the last couple of years for the virtual PASS summits, and I've been blogging at sqljared.com, and I'm way overdue for my next post. So I will try to get one up in the next week. So batching major operations. The purpose of this is to talk about how we can craft queries to take large operations and break them down into small operations that we can do quickly. This is most relevant for things like garbage collection, data archival, backfilling new columns, managing personally identifiable information to be in compliance with GDPR and CCPA, things like anonymizing, obfuscating, masking, encrypting data. And so, and in addition with that, you can even do take these techniques and batch really large queries or reports against an OLTP system. In my case, I've had to write one of those that returns millions of records in a reasonable amount of time without ever timing out. So this work all comes from work that I did a couple years ago at my job, and we were doing some work, and as a result of the work that I did, we were updating a bunch of data in our system because we were doing some PII management. We were anonymizing some personally identifiable information. And one of my coworkers saw the data coming into the BI system and said, some of these records are from like 2004. Are we supposed to still have these? Or are we supposed to have a data retention policy here? And what we found when we looked up through some of our processes is we had, say, garbage collection processes that are supposed to be deleting old data that were running and not failing or timing out, but they were running very poorly. And so this set off about 6 months where we went through and looked at a bunch of these operations and kind of got them back into shape, and found in some places we had collections of tables that didn't have any sort of garbage collection at all. And the result of this is we reduced the size of our database by something like 8 terabytes over the span of 6 months, maybe a little more than that. But there was an awful lot learned from this.
Holy, 8 terabytes?
Something
Wow.
like we were sitting above 20 terabytes at that point, and we've had other work going on since then, but we're close to like 10 terabytes now. So
wow,
yeah,
impressive.
we've
Impressive.
that was a really productive 6 months, but we've had more things going on since then.
Mm-hmm.
So the foundation of this is, to me, all of these operations. The way to take a big operation and break it down and make it a small, fast operation, a lot of the centers around the top clause, but also this is about the mechanics around the top clause and how we want things to work so that we can get these operations to run and complete quickly. So what should an efficient top plan look like? I've got a little example here. And we also need to understand the flow of how road mode execution operates. So let's talk about those two things. Here I've got a plan, and it's a pretty good plan. It's a simple select statement where you can see enough of the text to see that we're selecting 100 rows, we're selecting a few columns, we're going from the sales order lines table. And what you can see is in our execution plan, we've got us index seek against our first table, and we're returning 149 rows. We're doing a nested loops join, and when we go to, we're doing a key lookup. So when we're doing a key lookup on that table, we're returning another we're returning only 100 rows. The estimates here are a bit off. That information goes up to the nested loops operator, where we return only 100 rows, and then that goes into the top operator in the select. So this is one that looks good to me because we've got we don't have any blocking operators, we don't have any sorts or anything like that. We're not reading obviously a ton more rows than we actually need to return. We're doing a seek, we're not doing a scan, basic things like that. But also, so understanding the flow of row mode execution, what is so efficient about this? It's important to know how the query actually operates, and how it operates is the select operator is really driving everything. And the select operator basically says to the operator below it, okay, give me a row. In this case, that would be the top operator. So it tells the top operator, give me a row. And it doesn't care how the operators under it do whatever it is that they do. It just says, give me a row of data. So the top goes off and it basically says the same thing to nested loops. Hey, give me a row, which then goes down to the index seek and does the same thing. The index seek processes as the seek should with the index in question and the filters in question, and it returns the first row up to the nested loops operator. The nested loops operator is going to then ask the key lookup, okay, give me a row that matches this other row I've got. So it's going to be joining the data together from the two tables. So as it's joining things together, it's going to be passing the rows up to the top operator above it. And at each point, basically, the top operator says, okay, give me another row. And everything is happening in this fashion. Now, at the point the nested loops operator returns row 100 to the top operator doesn't ask for any more rows. And it's passed on everything it has to the select operator. And because the top operator doesn't ask for any more work from all the operations underneath it, the whole thing shuts down. And that's how we complete our query and how we complete it quickly. But there are some common caveats and some things that we're looking for when we're writing this kind of operation that we need to keep a lookout for, so that we don't end up doing an awful lot more work than we had intended. The first thing is blocking operators, in particular sort operations. And there's some other things in how we write it. I think of it as either misaligned queries or having conflicting criteria, however you want to say it. So what are blocking operators? This was actually the first blog post I ever wrote. And the reason I wrote it is we had a guest speaker, a guy come over to work for one day, and his name was Grant Fritchie, and he was actually the head of the PASS organization at this time in like 2019. So we were talking about Query Store and some other things with him, a lot of performance topics. And at one point he was discussing something, and we were looking at a specific execution plan, and he said, okay, and it's going to work in this way, but of course this sort is a blocking operator. And I was like, it's a what? And I literally don't think, after 10 years of working at Microsoft and a couple of years of working at Channel Advisor, I don't think I'd ever really heard anybody say the phrase blocking operators. So we talked about that some, and I go off and do some reading on it. And this actually ended up being my first blog post. I've got a link to it here in the slide deck. And we'll have the slide deck available. I actually have that shared up on GitHub. So we'll tell you how to get to that later. So I did a post on what blocking operators are and what they do. So blocking operators are a problem because they interrupt the normal flow that I was just talking about. One row going from this operator to the next, the top operator asking for more data, all of this happening in a smooth fashion, really one row at a time, gets interrupted if we have a blocking operator. And the prime example is a sort. If you have a sort in your execution plan, it can't operate on a row by row fashion. It just can't. You can't do top 100 with a sort, because the only way the sort is going to know which are the top rows is, well, it has to get all of the rows so that it can then sort them, so it can tell you which ones are the ones at the top. So if you're trying to do an operation like this, a bite-size operation, something that's just going to operate on a small set of data, you can't have this a sort operator in it, at least underneath that top clause, because what it's going to do is require you to read everything rather than just stopping at the first 100 rows. A second would be any hash match joins. Hash match are blocking operators, but only on the first table, the one that it's doing the build input on, because it's got to build a hashing table, but it can't do that one row at a time. It has to look at all of the rows that fit the criteria on that table, build the hash table, and then it can go and probe the second table, and that one it can do in a row mode fashion. It can operate on that normally, but you're going to do more work on the front side of that hash table than you would if you were doing, say, a nested loops join. An eager spool is another one. This is something I think really comes up primarily with the Halloween problem, which I can talk about a little bit as well. But this is a way for an eager spool is a table spool where the SQL Server is kind of trying to separate the select side of the query from the data manipulation side of the query. If you're in an update statement, the actual update operation. But an eager spool basically forces us to take all of the data that's in the operations downstream and complete those operations so that we have all that data at once, and that's our spool. And then we operate with whatever the remainder of the query operates on what is in that spool. Any kind of remote operation. So if you're doing a query to a linked server, whatever it's doing over there, it's going to complete that whole operation and then bring your data here. And hopefully you're at least doing predicate pushdown, but a top operator isn't going to allow you to short circuit that at all and complete faster. Scalar aggregates that don't have a group by, but the main things that you're going to run into is sort operations, definitely, probably hash matches, and maybe eager spools sneaking in sometimes. I've also got a link here about blocking operators. I think it was a forum post that Grant Fritchie commented on, but also Paul White, SQL Kiwi, commented on. So there was a little bit more information in that post about what else constitutes a blocking operator. So we've talked about blocking operators and we've talked about sorts. The third thing that I mentioned was conflicted criteria. Typically, we use an index for one of two reasons. If the index is matching the filter for a given query, then obviously we're going to use that query to just see the things that we want to read, and that's why we're choosing that index. But also, indexes can be really helpful if we're searching for things in a particular order. Our index already has the data in the order we requested. So we might choose to use a specific index because of the order. Now, if we are filtering on one field or column and we want things in order based on another column, we can only use one of the two indexes. And either way, that's not going to work. So it's a thing to keep in mind, is that if you're going to have a specific order that you want in your query, in your operation, you probably want that to be part of the filter as well, so that you can be filtering on that at the same time you're ordering with it. Then you can hit one index and get everything you want. But if you have a situation where you're trying to filter it and order it on two different things, it's going to pick one index or the other and probably scan it regardless. So let me go and do some examples. I've got a couple of things to go through. I have just restored my database. All these examples are based on the Wide World Importers database, so you can get my example scripts with the slide deck if you want to look through these and look at these examples. So I'm going to create a couple of indexes in this database that I have restored, just to make things behave nicely later on. All right, now here's a simple example. Actually, this was, I think, the example in my slide deck. I'm doing a query from the order lines table, and I'm filtering on the order line ID and the unit price. And our I didn't need that highlighted. And okay, this is a simple example. We're not even doing a key lookup for this query, but this is an example of what we expect to see with a query that's using a top clause and everything's going well. We're doing a clustered index seek on 100 rows. You can actually see here that we read more than 100 rows, but we're filtering things out. So we're reading some additional rows, finding out that it doesn't match the predicate, and then we're throwing those away. But the seek operator only returns 100 rows. That hits the top operator, and at that point, we shut down the query and we don't do any more work. There's more things we could have read based on this filter, but because of the top clause, we're done at that point. Get rid of you. And my next example is probably the one that we saw earlier in the slide deck. this is a pretty simple, now this is a pretty simple example, and you'll notice because I was talking about sorts, we actually do have an order by clause here, but we're putting it in order by order ID, but the order ID is also in our where clause. So in this case, yeah, we strongly want to use an index that actually has the order ID in it. And what do? We hit a non-clustered index on the order lines table. We return 149 rows. Some more of those get filtered out when we go and do the key lookup and do some additional filtering. We return 100 rows and we stop at that point. Now, here's an example where things get a little more interesting. Here I'm joining from the order lines table, the orders to the order lines table, and we've got something else going on here. So if I zoom in, here we're doing a clustered index seek and we're returning almost 5,000 rows. Why? Well, our where clause is looking for anything below a certain order ID and a quantity in the order above a certain level. So we're doing a hash match because the optimizer thinks we're going to return a lot of rows here. So the first part of the hash match, we're returning 4,999 rows. This is excessive. But like I said, this is a blocking operator. It can't build the hash table it needs to do the hash match join unless it reads everything that matches the filter criteria. So it's reading almost 5,000 rows, way more than we need, so it can build that table. Now the second operator is doing differently. We can actually see that it's only returning 900 rows. That's still more than we asked for. Why is it doing that? Well, what's happening is we're taking the rows in from the first operation, we're doing a clustered index scan, another red flag, but we're doing a scan, and we are additionally, you can see that we're checking the predicate later on. We're checking the order ID and the quantity. But we actually end up returning 900 rows from this operation, and that doesn't make a lot of sense. Well, the reason is, even though you can see that the actual execution mode for this operation is row mode, the hash match operator above it is in batch mode. So batch mode operates a little bit differently. And SQL Server basically, instead of the hash match operation asking for one row at a time from the operation underneath it, it just asked for 900 for a start. So that ended up going to the hash match operator. It returns 900 rows to the top, and the top takes the top 100, and then we're done. So this is an example of what happens when you have a blocking operator in your execution plan. And here's one more example. We're going to filter on the order ID and the quantity, but we're also going to ask it to give us the top 100 based on the last edited win date. And nope, that was highlighted. Let's try that again. So in our execution plan here, you can see that we're scanning the table and we're returning 11,000 rows out of this operation. This is what conflicted criteria looks like. We're filtering on one thing, but we're trying to sort it by everything else. Well, how is it going to only stop at 100 rows? Well, it can't really do that because it's looking through one index to try and meet our criteria, but then it's got to stop and sort everything before it can really get to the top operator. Now here we actually have a top in sort. So we're sorting the details and then throwing away everything after the first 100 rows. But the point and the problem here is we read 11,000 rows, or we returned 11,000 rows. We actually we read 500,000. We returned 11,000 rows, and that's a lot more than we were intending to get from this query. But the problem is we phrased this badly, our request. If we want to find things that meet this criteria, we probably shouldn't really care what order it's in. And once we do whatever we want with the first 100 rows that match our criteria, then we need to go find the next 100 rows. Any questions so far?
No, I think it's good so far. I'm learning some things. I didn't realize that about top.
I always thought it was a relatively simple thing, but it turns out there can be a lot going on in here. And again, these are things I learned from us going back and looking at our old garbage collection processes and finding out what was wrong and why things were, were so very far behind. So a simple garbage collection process. So let me give you a simple procedure. So there's a table in Wide World Importers called the vehicle temperatures table. And I'm just going to look at that and tell it, hey, let's try to get rid of things that are older than 50 months. So here's some example code. I've got a temp table. That table is based on a vehicle temperature ID. I want to do a batch of 100 rows. So what I'm going to do is I'm going to put them into a temp table. I'm actually putting an index hint on this because even with this index that I've added, SQL Server, the optimizer is a bit, it keeps coming up with bad ideas. It keeps coming up with bad ideas how to, it ends up doing an index scan a lot of the time when running this. I, for one, am not particularly shy about putting index hints on things when I'm having difficulty getting a plan that I like. So I'm going to put these rows, I'm going to put the vehicle temperature ID into a temp table, just one batch. I've got a top clause here in my insert select, and then I'm going to delete any of the records that are in that temp table from the main table. And I'm going to roll back the transaction just to keep my example here. So let me run this real quick. Now, because I've created an index and because I've hinted it, we've actually got a really simple example of a statement here. We're doing an index seek on vehicle temperatures on the index I specified. We're returning 100 rows. We're doing a scalar off of that. Well, that's probably date math. And then we're hitting the top clause, and then we're done. And we're putting that data into our temp table. Let's see, how many rows did we actually read here? Does it actually say? I'm not seeing it. It's estimating a lot of red, but the estimates are probably off. That's why we get bad plans. So and then we delete, and we're doing a scan here, but we're scanning the temp table. That's kind of expected. I didn't put an index on it. We're going to read everything there. That's fine. I'm fine with us reading everything in our temp table. And then we join to the base table. We do a nested loops join, and we delete our 100 rows. I didn't actually put a top clause on the delete itself, but joining to the table, to the temp table, is kind of like having the top clause there anyway. So this is a simple garbage collection process. If we went through this and completed the transaction, we would have just deleted 100 rows out of the table that's older than whatever our retention period is we specified. But we can actually make this simpler. In this case, I'm going to begin a transaction still. I'm still going to have a batch size, but I'm just going to have a delete with a top clause on that vehicle temperatures table, and I'll roll it back afterwards. But I'm going to leave in this index hint, and let's see how this looks. All right, we have an index seek. It's in row mode. The underlying table is actually memory optimized, so this is a bit of an oddity. Estimated number of rows. I don't actually see how many we read outside of 100. But we can see the actual number of rows for all executions is 100. That hits our top clause. We delete it. We're done. That's about as simple a GC as you're going to see. But now, if you've got one and it's nice and simple and the execution plan looks good, well, you could definitely decide, well, if we can delete one batch quickly, why not delete a few more? Here, I am adding a loop. I'm saying I want to have a batch of 100 rows still, and I'm going to have it run for 5 seconds. Let's see how many rows it can delete in 5 seconds. And I'm going to set an end time for this process because after we get to that end time, we're going to stop looping. And we're going to calculate the end time to be now plus duration seconds, 5 seconds. Start a transaction, and I'm going to say while we have not reached the end date, let's do our delete, let's do our batch size, and if the row count at any point is 0, so if we didn't actually delete anything, we're going to break out of this and stop looping anyway. So let's see what this looks like. This will take 5 seconds to run. I've got this deleting everything that's older than 180 days, which probably should be everything in the table at this point. So how many batches do we have? We have query 1. Let me scroll down. we probably did, we did 44 batches, so we deleted 4,400 rows in 5 seconds. That's not bad. I will take that. And there's a couple things we can, this is pretty simple. You could easily take this and actually make it a stored procedure that you can just call, pass in a few parameters to specify the batch size and how long of a window you want it to use. One other thing is some things occur as you start looking at these and working with these kinds of coding patterns multiple times. It makes a lot of sense that if you haven't deleted anything, then you obviously don't need to keep trying to delete things. But you also realize, well, if our row count is actually less than the batch size, if we told SQL Server go delete 100 rows and it can only find 90, then you're already done. And you can actually break out one loop sooner. So that is a simple garbage collection process that you can actually make a stored procedure out of and run as actual code. So there were a lot of things I learned from going through and looking at our old processes and finding out why they were performing poorly and looking for little places to optimize things. The first thing that I came to was keeping it simple. Things like the conflicted criteria, that doesn't happen if you don't say, put on an order by clause that's unnecessary. Don't have anything in the query that's unnecessary, and by all means test everything we do here. So in my example with the select statement that had a where clause and an order by that didn't match it, let me ask the question, if you're trying to say GC old data out of your table, do you really care, if you don't care about any of those records, do you really care what order you delete them in? Probably not, in which case having it sort that data is A, killing your performance, and B, unnecessary. What is it giving you? It's not really giving you anything. So get rid of anything that you don't need to have. The simpler we make these queries, the more efficient I expect them to be. I had a transaction in my process that I was just looking at that was looping. One of the things you can do is you might not always need transactions. A lot of my talking about this is I'm talking about garbage collection processes, and we'll talk about some other things. There are other places where you might want to do repetitive bite-sized operations like this and want them to be really efficient. But a lot of the work that I've seen with this is garbage collection, and it makes an effective example. But let's say that you're trying to delete stuff from multiple tables. Well, then the initial thought is, yeah, we need to have a transaction wrapped around that. But really, do you? If you get through deleting data from the first 4 tables and then you have, say, a deadlock and your session gets killed, do you really want to roll back the transaction and put the data back into those tables so that you can come back and delete them again later? Well, I would say it depends on what is the application going to see. If it sees that there's no data in the first 4 tables, but in the other related tables, data still exists. Now, if something's going to look at that and throw an error, then yeah, you probably want to keep the transactions. But otherwise, you might not need a transaction at all, and you can just say, hey, we got through part of that data, and then we hit a deadlock, fine. We'll get the rest of it on the next run. Another is to look for opportunities to consider an operation done. In my case, I was doing a top clause, and we were deleting 100 rows. Well, if we're not deleting any rows, we don't need to keep operating for the next 5 seconds. But if we're not deleting 100 rows, then clearly we should be done, and the next run is just going to delete 0 rows anyway. So if we can't get a full batch, then we must be done. Great. Hey, let's take a break. I pointed out in one of the queries that we had a scan, and that's something to key in on. Now, in that operation, the scan wasn't really causing a problem. We were still using the top operator. I think it was the one where we were operating in batch mode. So it had read 900 rows out of the underlying table. But here's the thing. Consider the negative is what happens when you don't return any data. If your top operator, if you're running your query and it's reading through the table, when it hits the first 100 rows, it will return those 100 rows and stop. Well, what if it doesn't find anything that matches that criteria? So it's going to keep reading. Now, if it's not doing an index seek, then it doesn't it's not intelligently looking for the criteria you're specifying. If it's doing a scan, it's going to read everything in that index. And if there are no rows that match the criteria anymore, you're going to be in a weird situation where not only is this operation is probably going to get slower every time you run it because it has to read more and more and more of the index as you are, completing the earlier records. But eventually, when there's nothing left that matches the filter for this process, you're eventually just going to search the entire index every time, return 0 rows, and that's just that's a lot more work than we have to do. So always consider the negative, and the main thing with that is if you see a scan operation, even if it's efficient right now because there's still data that it's hitting quickly. It's not going to stay that way, so we want to make sure we get those scans ironed out. Test your batch size. You might be surprised at where the efficiency would be in a given operation. The first thing I wrote like this that was leaning heavily on the top clause and trying to get a piece of an operation done was actually a big select statement. It's basically doing a large report. And when I was testing this, I tested it out to see how large I should make my batch sizes. And I was really surprised at the results. I tried, okay, let's get 100 rows. Okay, would it be better if we did 1,000? What about 10,000? Out of those three, 10,000 was the most efficient. It took longer than getting 1,000 rows, sure, but it didn't take longer per row. We were getting 10 times as much data, but taking 3 times as long. So that was more efficient. I actually tested larger sizes from that, and 10,000 seemed to be the sweet spot. Might not match your preconceived notions, so check that because it really might affect how well your process performs. And the second is just, the last one is just a parameterize things, as I did in my last example. If I have a particular process that we're cleaning up data in a given area, on occasion, I might find out, oh, we've just gotten a big influx of data on this database. We probably need to run that GC more because that account closed. We're going to have a lot of data there to delete. I could call the same stored procedure with a larger batch size or with a larger window. Tell it, oh, no, just run 60 seconds. Don't run for 30 seconds. Let's run for 60 seconds, and we'll probably be caught back up by tomorrow. So having parameters in your procedures you're running for something like this gives you flexibility for later. All right, let's look at another GC process with a little bit more to it. If I can get to Manager Studio, there we are. So here's one that's more complicated. This has a number of tables that are all related to each other. So this is again in Wide World Importers. We're going to do a GC on the orders table. So I'm using 2 temp tables here. One to track order IDs and one to track invoice IDs, which will become apparent shortly. I've got a batch size, I've got a duration, and I've got a retention period as another parameter. So how long are we retaining this data for 50 months? So anything longer than 50 months, anything older than 50 months can go away. Great. Now, I mentioned transactions too. One of the things about my previous example is I had the transaction outside of my while loop. So that would have also meant if anything happened, if we hit a deadlock or something, 40 loops in, well, we would have rolled all of them back, right? It's probably not how we want to do this. If we do end up in a situation where we want to roll back a transaction, especially if we're looping, we probably want that transaction to be inside of our while loop. So let's make sure our temp tables are empty. I check to see if there's a transaction already by whatever called this stored procedure, and if there is a nested transaction, we don't create another one. Now, I want to find the top batch size of rows from the orders table just based on the date. Give me anything that's older than our retention period. Give me 100 rows. We'll throw that in the temp table. We'll have the order ID. Well, why do we want the order ID in the temp table? So that we can join to other tables that are related to the orders table, and any order ID in the temp table will go away in those other tables as well. So the order lines table is related to the orders table based on order ID. So once we have our batch of orders, we can then go and delete all of the related records in order lines based on the order ID. Simple enough. And the next statement I'm actually doing another select against the invoices table. The invoices table is related to the orders table based on order ID. But there are other tables related to it that all have foreign keys. So we can't just go deleting from the invoices table. We need to find out those invoice IDs so we can clean up its related tables as well. And you'll notice here there's a comment. I have the top clause here, but I have it commented out because we really don't need it anywhere besides the first operation. Like the orders table, we've got 100 order IDs, but order lines is going to be a one-to-many relationship. One order could have many order lines. So we don't want to delete top 100 here. We would only delete part of the rows related to those orders. So, and likewise, we don't only want to delete part of the invoices. Now the invoices might be one-to-one here, I don't know, but if we're joining from the temp table that only has 100 rows, let's just go ahead and get everything that's related to those 100 rows, whether it's 100 or whether it's more. But we don't really need the top clause here, so that's why that's commented out. We're going to take those invoice IDs, put them in a second temp table. Then we're going to delete from customer transactions, stock item transactions, and invoice lines based on what is in the invoices GC temp table. Once we've deleted all of those, and I indented them for a reason, then we can go back and finally delete from the invoices table based on the orders GC temp table. And then we can finally delete from the orders table itself. If we don't have a nested transaction, we'll commit our transaction for this loop. And then we'll loop and we'll do it again. So I'm going to do that, and I'm going to have this run for 5 seconds, and we can take a look at the results. All right. So let's take a look at some of these. Here we're inserting into the orders GC table. We have a constant scan here. This is really just our date math. We're doing an index seek. We're returning 100 rows. That's going up through our join and our top clause, and we're completing pretty quickly. Does this tell us? Yeah, number of rows read 100. First 100 rows we read met our criteria. We didn't do anything else. Next, we delete from the sales orders invoices table. No, the order lines table, say order lines table. We're doing an index scan against our temp table, but I know that's only 100 rows, so I'm not offended about that one. We go and we look at the order lines table, and we actually are deleting 215 order lines. There's not a top operator here. It's being limited by our temp table. So there are 215 order lines related to those orders. So it's a good thing we're not using a top clause. We have and the 215 flows upstream. We delete from the clustered index. There's a column store index as well, but we're getting through this without any real problems. Next, we insert into the second table based on the invoices table, and you can see the invoices and orders are one-to-one because we're only returning 100 rows, even though we don't have a top operator. We delete from our other 3 tables related to invoices. These are all using index seeks. We have a sort here, but again, we don't have a top operator in this operation, so it's not really hurting us. Everything's being limited by the fact that we only returned 100 invoices. We get through those three delete statements. Then we come back and we delete from the invoices table. Now this one's there's a lot going on here. Why would that be? Let me scroll over here. So we have an index scan on the temp table. We're hitting the invoices table, 100 rows, nested loops. We're sorting those, everything's fine. And then we hit customer transactions, invoice lines, and stock item transactions. Well, why is that? It's because of this assert is your key here. If we're deleting records from invoices, we have to make sure that we're not violating any foreign keys. So we're checking these other tables to make sure we're not doing that. And that's what the assert operator is for later on. If we had any rows coming back from those, we would fail the operation because of the foreign key. But row counts and everything looks good. Our operations look good. So we're staying pretty efficient. And then we're going to delete from sales orders. This is also a large plan, but we're doing some of the same work here in that we're checking order lines and invoices and doing an assert to make sure we're not actually violating any foreign keys. We also have a second assert here, and I think it's because there is a foreign key from right. The backorder ID is related to the order ID in the sales orders table itself, so it's related to itself. So it's checking that foreign key as well. But we went through all of those, and then we started looping. Here we're populating our temp table again. So we have 8 statements in a loop, and we did 5 batches of this in 5 seconds. Not great, but those foreign key operations and checking those out in particular, I find that those seem to be really expensive. So that's an example of a fully fleshed out stored procedure that is deleting from multiple tables. So we've been mainly talking about deleting operations so far, and that's been my examples. But let's talk about updates. So why would you need to do updates of this kind? My main thing is dealing with GDPR or CCPA. So if you're needing to deal with personally identifiable information, what are you going to do? You're probably not going to go through and delete records, but you're probably going to go through some of your tables and look for specific kinds of data and anonymize them or obscure them or encrypt them or whatever. So fundamentally, you're updating. This is a process that's ripe for the same kind of logic because that's going to be an ongoing process, right? You're going to need to anonymize data that's more than a certain age. You're not going to delete it, but you're going to need to have this as kind of a scheduled process running in the background. You're always going to need to do these kinds of operations going forward. There is one big thing that's different about them. Is it's very easy to have updates that operate progressively slower. So I like to think of delete operations as being self-cleaning while updates are not. So think about it like this. If you go into the orders table and you want to delete 100 rows, you find the first rows that are outside of date, you delete those rows. The next time, you're not going to see those 100 rows again. You don't have to read past them to get to the next 100 rows that you want to delete. But if you're updating data, you're going to go find the first 100 rows you want to update. You're going to change them so they don't meet your criteria anymore, or so that they've been anonymized, what have you. The next time you run it, if you're using that same index, you're going to have to read those 100 rows again and say, oh, wait, those have already been done. Let me get the 100, and you're going to end up reading 200 rows to actually find 100 for you to operate on. And there is an answer for that, and that's filtered indexes. Let me go to my example here. So let's look at the invoices table now. And I'm going to drop an index on that table, and I'm going to build an index on the last edited win date. So we're going to be able to find quickly the oldest things in the table, and we're going to include delivery instructions. So if you're anonymizing data, largely I find myself looking for any kind of text field, any kind of invar whatever field, because there could be anything in one of those. Even in delivery instructions, you don't know, somebody might have a note they might use a name, you might see a relationship. There could be anything that this is written by the customers. So the delivery instructions could have anything. So let's just be safe and make sure we anonymize that data. Whenever I'm going to do a delete or an update, I'd like to start off by making sure I can write a select statement that's going to perform well. So let's do that. I'm going to do a batch of 1,000. Let's see if we can return 1,000 records, their invoice IDs and their delivery instructions. If the record is older than 90 days and the delivery instructions are not null. Okay, we've got a constant scan. We've got an index seek that returns only 1,000 records. Nested loops, filter, top, great. This looks simple. This execution plan looks fine. So let's do a loop where we're going to delete batches of 1,000 this time. We're going to keep track of how many rows we're updating, and instead of looping for a certain number of seconds, I'm going to say, let's just delete 50,000 rows. We do that and we will call it a day. and I'm rolling back my transaction here because I don't want to mess up the example. So 50,000 rows, how long is that going to take? Probably substantially slowed down because I'm actually asking it to give me the execution plans. But this is a good example of what I was talking about. So we've got our constant scan. We hit this index that I just created. We're getting 1,000 rows. It's going into our nested loops. We have another filter up here. Okay, what is that filter operation anyway? We are filtering here that the delivery instructions is not null. Okay, I don't know why we're not doing that on the index itself, but sure. We have a top operator, then we go through, we update our index and we update one of the other indexes, the primary key, the non-clustered index, great. If we look at the next one, this is where we start to see things going wrong. We didn't return 1,000 rows. We returned 2,000 rows from our index seek. And then it goes up here to our join, and the join returns 2,000 rows, but then the filter only returns 1,000. This is what I was talking about. The filter is on delivery instructions. So if the delivery instructions field is not null, we filter those rows out. So we read 2,000 rows because the first 1,000 we filtered out here before we got to the top clause. So we had to go read more rows. So our second operation, we ended up reading 2,000 rows, and then 3, and then more, and then more. Wait a minute, 49,000. In any case, before we got to the point of actually reading, deleting our 50,000 rows, we would have had to read past 40,000 rows we had already updated, already anonymized, but we would read those here because they're still in our index. And we would read them every time we ran this operation ever from that point on. And then finally, we would get down to the point where we could return, we would be returning 50,000 rows, filtering down to only anonymize 1,000. It's a lot of work we don't need to do. So how do we deal with that? What we do is we need those records as we're updating them, we need them to go out of that index, just like when we're doing a delete operation. So the answer to that is, let's put a filter on our index that we're intending for this operation. Let's filter it so that the index only has records where the delivery instructions aren't null. So now this index is going to have only records that need to be anonymized. So now if I go through and I do the same thing again, thousand rows read, 1,000 rows read. Scroll way down, 1,000 rows read. Not cooperating. That's only query 3. Oh, that's because it was still running. Operation 50, 1,000 rows read. So, and just as a throw-in, when we're doing these kinds of queries, you might have a lot of queries that are based off of inequalities. If we're looking for older data, either to anonymize it or to delete it, we're going to be comparing against a date, and you're never looking for an exact date. You're always looking for something that's greater than or less than a given date. So one of the things that you might run into that will lead to you having a bad plan and possibly a sort or maybe a hash match or some other kind of blocking operator that's going to really crash our performance is the 30% estimate. So what is the 30% estimate? This is kind of when SQL Server doesn't have great stats to work with, or for some reason it can't use the information to make a reasonable estimate of how many rows it's going to encounter on a given operation. It has kind of default estimates. If you're doing an inequality query and it doesn't have useful stats, and it may only apply to local variables or other specific circumstances, the SQL Server is just going to estimate if it's an inequality. It's going to be like, they'll probably read a 30% of the table. That's actually a really large amount. That's a significant chunk of the table, at which point SQL Server may just decide to do an index scan instead of an index seek, even if there is a good index for it. So this is one to be aware of. And it may be less applicable to complex queries, but I'm trying to write simple queries for this anyway. But a more complex query, if we're joining multiple tables together, or we have multiple criteria or multiple variables, there's more things for SQL Server to work with, and it might be able to estimate based off of something else that's going on or start its query on a different table. But if we have a simple query that we're doing an inequality, it very well might default to that 30% estimate. So let's do one example for that. Here, I've got an archive date, and I'm setting the archive date to be 70 months in the past. So let me run this select statement. And let's see. This says I've got 76,000 rows within date. Great. Now, and it read about 76,000 rows. You can see in the execution plan, 76,412 here, 76,325 here. So our estimates are pretty good. Now, you might have noticed I made a mistake here. I went ahead and I set the archive date and put it in a variable, and then I just did the same date math here in my query. So let me actually flip that comment back out, and we'll actually do the same query, but we'll run it this time based on the archive date we calculated in our variable. And, oh, I did declare it. Keep highlighting things. Okay, we still returned the same number of rows, but if we look at the execution plan, our estimates are way off. We returned 76,000 rows, but we only estimated 47,000. That's way off. A minute ago, we were right. Why were we wrong this time? And the answer is we were making a blind guess. When we were basing that query off of a variable, well, variables don't have statistics. So how large is this table, and what is 30% of that table? Well, this table is 158,000 records. And so if we were to estimate that we'd be reading 30% of the table, that would be 47,636 rows. So part of the lesson here is if you're doing processes like this and you're doing an inequality query, you may get this execution plan. And because the SQL Server is estimating you're going to read more of the table, you might get a different plan. In this case, I didn't. I'm not getting a scan or anything complicated, and this is a very simple query. But we're not getting an index scan. We're still getting an index seek, but the estimates are way off. In a different circumstance, this might actually come back and bite you. Well, one of the things I can do here is if I'm comparing the order date, or if I'm looking for the order date based on a variable, SQL Server doesn't have anything to work with, doesn't have any statistics that it can use, but it can use statistics about the date column if it's calculating this number on the fly. Here it comes up with the right estimate. Here we're not actually storing that data in a variable, we're doing the date math live, and we're getting a note in our execution plan for that, but it doesn't appear to be expensive enough to cause any problems. But we end up with an accurate estimate, so I would rather write my queries to do the date math live, because I think we're going to end up with better estimates, and hopefully we'll be less likely to be surprised by the execution plan. And that is all of my examples for this. So for the examples, I've got them and the slide deck. I've got them up on GitHub. I've got a GitHub page at SQL Jared, and I am sure your leader can send out a link to that if she wants to later on. But if you want to go through any of the examples of this, they're all based on the Wide World Importers database, which you can download for free, of course. But you can run through the examples. I've kind of got them numbered based on what they're about. The ones that start off with a 1 are just showing basic examples, showing how the flow of those queries work with the top plan. The comprehensive garbage collection processes, what it's like to do an update and why you would want to do a filtered index. And lastly, that inequality estimate example, that might be one you'd want to show to somebody. If you have any questions, you can hit me up on Twitter at SQL Jared. I also have a blog at SQLJared.com. I blog on basically just performance topics. but I've been doing that for a couple of years. I've been taking it easy so far this year, but I'm going to try to get back up to my usual cadence and maybe do a post every couple of weeks.